Good morning. Thank you very much. Okay. Right. This is sort of what we're going to talk about this morning. We're going to start off just with a little bit with some of the challenges. You all know them, but I find it's useful to remind ourselves periodically, because I know as a technologist, sometimes I get so excited about the technology, I forget about the business problems that I'm trying to solve. And then we'll go into a little bit of an overview of the database, and then we'll talk about the actual cluster technology, and then the differences between TED and Postgres proper. So, the database challenges. After 30 years of development, RDBMS systems and IT infrastructures in general continue to have problems. And we keep adding new products, adding new solutions in order to try to help us solve two key critical issues: availability and system performance. Some of our customers tell us that an hour of downtime can cost them in excess of $100,000. So this is a very expensive problem that we continue to solve. Another customer tests their failover, their DR site, every month. And every month, something has gone wrong with the DR site that prevents it from being able to come up, whether someone has forgotten to keep all the various pieces of software at the appropriate levels, whether someone's forgot to move the latest change to an application program over. Things continue to fail, and that continues to cause failure. And of course, performance is always a failure, no matter how fast we make our systems, how much data we make them capable of handling. People continue to push for more and more performance. And in today's world, things are complicated by the fact that now we have customers coming in and at our systems, customers and users coming at our systems from all over the world. Okay. And when we have a failure, it can not only be costly to the business, it can be an embarrassment when it hits the front page of a paper. And if you're the one that gets tagged with being responsible for that, it could be more than just embarrassing. And so we've done a lot of things to try and solve the problem. We're adding piece parts, and we've noticed now that people are trying some new things, distributed high available solutions, sort of Hadoop-based, but for critical applications. Jacob mentioned in his keynote yesterday that he thought we were on the verge of the next great wave of technology in technology. And I agree with him, because we see all the indicators in the marketplace. When you start to see things like lots of different vendors, lots of different new solutions trying to attack a problem, and you also at the same time see a lot of the old guard standing up and saying, yes, we've got a problem. And we're seeing that today. We're seeing a lot of Hadoop-type solutions to try to come in and say, no problem, we can handle your enterprise systems and we can keep them available, highly available at all times, because your problem is SQL. And then we have the old guard who's coming along going, wait a minute, SQL's not the problem. We need ACID. What the problem is are these 30-year-old RDBMS systems that were built for outdated architectures. And we see that Michael Stonebreaker is currently working on a distributed solution, VoltDB. Jim Starkey, he's now working on NuoDB. So we see two camps, and that's typically a sign that there is going to be a huge technology shift. Now, some of you might be saying, but wait a minute, everybody I know is going to a consolidated data center. And we tend to see opposing signs in the marketplace right about the time we see a technology shift. There are laggers, or people that tend to be more cautious, risk-averse. When they start to notice problems with their DR solutions, their remote sites, they're going to pull those in and say, okay, I'm going to solve my problem. I'm going to pull everything close. I'm not going to have anything remote. So we see that on one side, and like I said, we see the other side going, we're never going to solve the problems that we have today, and we're never going to solve the problems that we're going to continue to have into the future unless we distribute, unless we move our solutions out closer to our customers. Okay. So who's right? Like I said, we've got these two camps. The Hadoop side saying, you don't need SQL, don't worry about it, and the business side. Well, the business side is pretty certain. We've got to also have that respect for data that Jacob mentioned yesterday. One of the things that Monty Wiedness, who created MySQL, is fond of saying is, if you're doing 1 million transactions a day and they're worth 99 cents a piece, it doesn't matter if you lose a few. And that's very true for that business, right? But if you walked into your CFO tomorrow or one of your customers and tried to tell them that, oh, if you lose a few transactions every now and then in your general ledger, don't worry about that, you'd probably be gone by that afternoon. Different business. So we definitely need ACID. So that is what TransLattice is about. We've taken Postgres and we've used it to combine the economics and scalability of cloud computing and distributed solutions for high availability and performance into one relational database whose intent and purpose is for mission-critical applications that require ACID semantics. So let me tell you a little bit about TED. Whoops. Hello, come on. Not this TED, okay? When we first came out with our product, the first product that we delivered was an application platform called the TransLattice Application Platform that was meant to solve a whole range of problems. When we went out and talked to people, people kept saying, tell us more about this database that you tell us about. Well, it was an internal core component. It really didn't have a name. It was just our secret sauce, our key intellectual property. When we kept getting pressed, and it sort of gets old talking about our database, the database. So we decided, since it was just a key internal component of our big solution, we would just give it a quick and easy name, mostly internal. So we came up with TED. And when we kept getting pushed by customers to make TED available as a standalone product, we said, okay, we'll deliver TED as a standalone product in Q2 of 2012. So this TED came 4 days after our TED. Okay? So our TED is a geographic scale-out solution built on Postgres. It has plug-and-play simplicity. You can stand up a 6-node geographically dispersed cluster within an hour and be ready to start loading data, loading your schemas and loading your data. I mentioned it's designed for mission-critical applications. We started this project in 2007, so we've come quite a long way. Took many years to get it to where it is today. We didn't come out of stealth until late 2010. So we started on Postgres 8, I think 8.4. I just joined the company in 2010, so I'm not sure. Shortly after I joined, we came up to 9.0, and then we're coming out with a release in the fall, in Q4, excuse me, that is now built and has integrated the 9.2 code line. So we're keeping current with the latest version of Postgres, and this also combines the Postgres-R technology. Okay. People ask us, okay, so if this is a geographically distributed database, what are you giving up with the CAP theorem? We are primarily a CA database. In a future release, we plan to introduce a transaction isolation level for eventual consistency that will allow us to, for specific use cases, also be an AP database. So, and TED is designed to run anywhere. You can run it on virtual machines. You can run it on an x86 commodity server, or you can run it in the cloud. And TED is designed to run on bare metal to reduce the number of failures that you have from external components. And that's a key differentiator with TED. We start with a bare bones Linux kernel, and then we integrate the components we need and a lot of IP that we developed for having the cluster communicate and combine it with Postgres into a tightly integrated node that can be easily deployed. We'll talk about each of these components in detail in just a few minutes. Okay. Okay. The software comes delivered as a single file, whether it's a single ISO or an OVA file, or if it's a cloud instance, we'll set it up for you by installing our file. Basically, the install is the equivalent of a tar file, a tarball. So it's essentially a one-click install. You install the software on your TransLattice nodes, and these now become what we call unblessed nodes. They've got all the software that it's required to stand up a fully networked, autonomous Postgres server. You then go into a web browser and connect to our user interface, which walks you through a short series of fields to fill out. Basically, what am I going to call my cluster? What kind of networking am I going to use? Am I going to use DHCP, or am I going to use static addressing? What's going to be the name of this first node that I'm blessing, right? And this creates a one-node cluster, right? Now, all the other unblessed nodes that are in the system immediately recognize that there is a TransLattice cluster in the area. It's on the same subnet, and it starts advertising that, hey, I'm available. Come and pick me up sometime. So one can then connect to our user interface. This is a screenshot of how to bless an initial cluster. And basically, it's 4 panels. You walk through the 4 panels. Like I said, fill out the information, and it goes into a state of processing that takes approximately 2 to 7 minutes to initialize all the software on the node. And then you have your one-node cluster. Okay, all right. You can then connect again and start connecting other nodes. And again, we've made this very simple. Because the nodes are advertising that they're available, you can go into the cluster, select the function, add a node, give the node a name. A drop-down is available. You can select the nodes that you want to add to the cluster. You add them one at a time and save them. And the cluster starts communicating, and existing nodes within the cluster agree or disagree to accept the next node. So far, there's no reason to reject a node. So one of the key ways in which the system works is through auto-discovery. So when you add a node to the cluster, it interrogates the platform that it's running on to find out how many CPUs do I have, how much memory do I have, how many disks do I have. And that's how the system generates its configuration file. It's by understanding what kind of hardware it's on. And then add nodes. As nodes are added to the cluster, he makes adjustments to his configuration and keeps the entire cluster in sync. And this system of Postgres TransLattice nodes, act as a single database server, and it looks to all users and developers as though it were a single Postgres instance. Okay, so one can continue to add the nodes. and this is really hard to see in here, but this is the representation that you get of the cluster within our user interface. So, and you can click on any one of the nodes are on the outer ring. This is showing, I believe, a 6-node cluster. The nodes are on an outer ring. You can click on them, and then you can go into a display, or the display on the top will switch to show you the specific information about that node. The way users connect to a TransLattice cluster is usually through what we call a service entry point. For those of you that are familiar with Oracle RAC, they have the concept of a virtual IP, and this is similar. This allows a layer of abstraction between the physical nodes and the users. That gives us load balancing across the set of nodes that's being serviced on that subnet and assigned to that SEP, and it also gives us protection from failure. When users are connecting to a SEP, the nodes that are being handled by that SEP arbitrate for control of the SEP. And they consider current workload on the system, current network, where that connection is coming from to determine who's going to grab and service that request. If the node that's handling that request fails, the user can simply reconnect again to the SEP, and one of the other nodes in the subnet will handle that incoming request. Okay. One of the key technologies that makes this all work is our global consensus protocol. The nodes work cooperatively. There is no master, there is no slave. All the nodes are capable of working in an autonomous manner, and all cooperate to work. Our global consensus protocol is based on a generalized fast Paxos algorithm, and we get our performance in a number of ways. One is that only nodes that participate in a transaction will work in that particular discussion between the nodes. Nodes communicate in a number of different ways. One is through virtual synchrony. I said, when you have lots and lots of users connecting to the system, you may only have a subset of nodes that need to participate in any given transaction to satisfy the query request. So when that happens, those nodes form a group and they communicate. We also use unicast communication for when a direct request is made of a specific node, and one I didn't list here is also multicast. I mentioned that when TransLattice nodes are available on your particular subnet, they are broadcasting that they're there and available, and they're doing that through multicast. If you have multicast turned off, the only difference is you have to add those nodes to a cluster by specifying their IP address and MAC address. Okay. So as I said, within the cluster, any specific transaction may only include a subset of information, a subset of the nodes within the cluster, the nodes that actually house data that are affected by that particular transaction. And this just quickly walks you through Paxos for those of you who aren't familiar with it. Because as I said, Paxos is how we managed to make this work and how we managed to make TED work in a performant manner. The system maintains a partially ordered list of all the transactions in the system, and this Paxos algorithm is running on the system so that when a transaction comes in, the request is sent to Postgres processes who then send the request down to the nodes to basically say, hi, I've got a request. Is this request valid? Can I do this update? Okay. The nodes then respond with a yay or nay. If everything's cool, they go back and say, yes, I don't see a problem with that transaction. okay? So the request is sent back to the nodes, say, okay, I want to write that data to the nodes. The nodes say, okay, I can do that. I don't have a problem with that. Information is sent back to the client, and at that point, the information is committed to disk. So TransLattice supports, this effectively gives you a global two-phase commit capability. You're ensured of consistency, and because of the way the system maintains these lists of transactions that are in flight, thousands of transactions can commit on one pass of the protocol. Other transactions that fail simply return back, oh, I had a failure, I had a conflict. Because it's built on Postgres, it uses MVCC, so it works exactly the same way. If somebody has submitted a conflicting transaction, you merely get a response back. And we'll talk more about that in a little bit. Also part of the underlying system is our networking component. Within the system, all communications between nodes are encrypted, but they're also compressed. Okay, so we get optimum throughput on the network. And our network subsystem is constantly monitoring latency on the network, bandwidth available, as well as load. So that information becomes part of what we use to do transaction query optimization and planning, right? Using our network information, and along with where data is placed on the cluster, we determine where to send transactions to. Okay. We also have an object policy and placement system that's built within the cluster, so that when you set up the TransLattice cluster, one of the things that you do is you say, I want to have n numbers of copies of my data spread across y failure domains. So what I try to do is I set up my cluster so that I have nodes in various regions, so that if I have a local failure, I still have a full copy of my data at other nodes within the system, right? If I'm in the US, ideally I would try to set up, one part of my cluster, on the eastern grid, and another part in the central grid, and perhaps a third on the eastern grid. And I tell this policy system, make sure I've got 3 copies, make sure they span the region. That way, if I have a failure, I still have a quorum of information available in order to keep operating. We have various types of rules that control where data is placed. One is the redundancy rules. I just talked about that. The second is locating rules, so that I can specify that data in certain tables or certain key ranges may not be stored on a specific node or must be stored on a specific node. This builds a lot of compliance directly into the database, right? So if I do business in Europe, for example, and I have a regulation that says any personally identifiable information that we generate must reside in the country of origin, we can tell our policy and placement system through our rules, and when that data is generated, it will only get placed on appropriate nodes. Okay. The other thing that we take into consideration is historical access patterns. Who's using what data from where? I said we start out with our redundancy rules, right? And we may put 3 copies out in the world across 3 different nodes. But we may find over time that some specific data is getting used in a location that we hadn't originally stored data on. We'll generate a copy of that and move it to that location to improve performance for the users that are coming into that node. Okay? Keeping in mind our locating rules. We won't place data closer to somebody if it violates our compliance policies. And the last thing we take into consideration when we're placing data on the system is what we call deterministic randomness, right? If everything is equal on the system, I've got my set of rules, my usage is fairly constant, I don't want the system always picking the same nodes necessarily to place things on. I want to use every available storage pattern within the system. So I may have a 3-copy policy, but I may have a 6-node cluster, right? So I want to make sure that data is sort of evenly distributed where possible across those nodes. So for that, we use a concept that we call deterministic randomness in order to achieve that. Okay. We maintain data by shard. A shard may be a single row of a table. It may be a group of rows based on key value. It could be an entire table. And as a matter of fact, sometimes we recommend that. If you've got small lookup tables that are less than 8K, why wouldn't you put them in a single shard? Why wouldn't you specify, hey, go ahead and put those, on as many nodes in the cluster as you want to? That would help performance, reduce traffic across the wires. Okay. And we're maintaining statistics based on the shard. So rather than table-level statistics, we have shard-level statistics. And we use those in our query planning, and we also use those for data placement. So these shards are invisible to developers, and they're invisible to users. Right? I'll show how we generate the shards in a minute, but when I address information in the TransLattice database, I'm using the base relation name from Postgres. And it's the underlying technology that says, oh, okay, these are the shards that relate to that base relation. We also use the statistical information for partition elimination, so we only pick up and involve shards that are required to satisfy the query. Okay. So all of that I've talked about so far is external to the modifications that we've made to Postgres in order to support this. This system essentially becomes a set of primitives that our version of Postgres depends on in order to place data. So you can replace our set of primitives with another set of primitives if you so desired. And the way we got to this point is by essentially building on the primitives that were in Postgres-R to expand and expound upon them to generate ours. Okay. So one more point on that. I mentioned that the system auto-configures. The system definitely is looking and expecting that all nodes are the same. All configuration changes are made through the user interface. Okay, so if you change something, that configuration change is automatically migrated across the cluster, so the configuration remains consistent. In that way, the system can continue to look like a single server. We may, in a future release, support the concept of a special purpose domain where we say, oh, this set of nodes is going to be used for more OLAP type queries, right? And we might then allow that domain to have a different set of configuration parameters that might be better suited to that workload. Okay? Okay, so I mentioned we started with Postgres. We get a lot of questions. Why did you start with Postgres? Some people say, why didn't you start with MySQL? MySQL's huge. I mentioned earlier, we need that asset, and we understand that enterprise businesses are relying upon that. And Postgres is a solid, feature-rich foundation for us to build on and get this capability. So we also started, again, with the Postgres-R, and that becomes the foundation of the product. Okay. PostgresR is an open source database replication system for geographically distributed nodes. It came out of research from the University of Science and Technology in Zurich. It was originally done by Bettina Kemme and Gustavo Alonso, and they have since turned over that project to Marcus Vanner. Marcus Vanner now works for TransLattice, and he would be here today giving this. Unfortunately, September is when he does his public service in Switzerland, so it's not a good time for him, but we're very pleased to have him on our staff and continuing to maintain Postgres-R as well as contributing to TransLattice. Okay, so I'm sure you're all familiar with this. We're going to walk through really quickly what then are the differences between TED and Postgres. Well, at the storage layer, it's very, very similar. There are a couple things that we don't support because we run on bare metal. We really don't support the PG ident, the ability to map OS users to database users. Conceptually, you only have database users on a TED node. PG serial is new with, I think it's new with 9.2. I don't recall seeing it under the 9.0 directory structure that supports the serial replication technology, which is at this point sort of antithetical to what TED does. So it's there. We don't use it. Don't expect anything to happen to it. The configuration files, instead of being true files as they are in a Postgres system, they're symlinks to the global configuration, right? And so if you make a change to the configuration, it's going into the global configuration that's being communicated throughout the cluster, and the Postgres instances on each node look to that, to where we store the information for that symbolic link on that node. Okay. The other thing you'll notice if you look at a TED directory structure is there's a file system called distributed. Within the TransLattice system, each of the nodes has physical storage associated with it, whether it's SSD or SAN or direct attached storage. And we have if you will, a hidden table space that's associated with that that's called TL disk, where the shards actually reside. But what users see is the TL distributed database, table space, which is, has a single consistent view across the cluster. Okay? So when you connect to a TransLattice node and you say, give me all the rows in the customer table, if the customer table has 100,000 rows that are split across 10 nodes in the cluster, you get 100,000 nodes. You have no idea where they're coming from. It looks to you like Postgres. Could have come off my local disk. By default, when you create objects in the TransLattice system, they are created in the distributed table space. The exceptions are if you say create temp or create temporary table, those are created in the default temp table space in Postgres, which is local. Okay. All right. So with the processes, there are some that we've modified. For example, the background writer is aware that this is a distributed system, and since the background writer is obviously a local process, when he gets an instruction that needs to be satisfied from a remote node, he knows to invoke a background worker on a remote node. Background worker is essentially a copy of the Postgres process, but his role in life is to satisfy a subquery and return a subset of data to the requesting node. Okay. We've also modified the wall writer. We have a concept of commit order ID that helps keep everything in sync across the cluster, so the wall needed to be made aware of that. The wall is local to the node, so there's not a whole lot of modification there, but it did need to be made aware of the changes. And I talked earlier about the statistics collection that we did. So the stats module has been modified substantially. Okay. All right. far as memory, it looks exactly the same between a TED node and a Postgres node. In the query engine, though, the parser remains the same, SQL, SQL. We want to keep all that. The path generator, though, has been modified. It needs to adjust the query when different portions of the data that need to be satisfied, are needed to satisfy that query, are located on remote nodes. And then we've added a distributed mapper process, basically turning this solution into a map reduce, so that if I've got bits of data that are spread out, the query is partitioned and sent to those nodes. Obviously, the optimizer has been modified to handle this somewhat as well, and then the executor. So, as I mentioned, when you get a query, we determine, okay, I've got data on 3 different nodes that are required to satisfy this. Requests are dispatched to those nodes, subsets are returned, and then the result sets are then reduced to provide the right results to the query. We try to position, as I mentioned earlier, data closer to end users. So response time is typically minimized because the query is happening typically closest to where it's being used. And we're also factoring in, as I said, the communication links between the various nodes. So we're using the optimum paths in order to satisfy any distributed query. Okay. I mentioned we didn't change the buffer structure, and we haven't, but in order to make TED work more efficiently, we have added some efficiencies to the buffer manager. Recovery manager, only one small change there. When a node comes up, as in Postgres, it goes through recovery, but the next thing he has to do is find out, oh, did I miss anything while I was out? If this node crashed and may have been down for an hour until someone was able to reboot him, there may be information that was stored on that cluster that is now not current. Data's still current, it's available on another node, so the recovery manager has been modified so that it will call our distributed recovery manager. And the distributed recovery manager says out to the cluster at large, hey, what did I miss? And they return back with information pertaining to only the shards that are stored on that node, what their current level is. If there's any mismatch, the node that was down requests of one of the nodes that has a copy of the current information to start updating it to bring him up to speed. This allows the distributed recovery to be amortized across the system. While this node is recovering, the system still remains fully functional because, as I said, we've specified on the system, I want n copies of data. And as long as I have a majority of those copies available, the cluster continues to operate in full read-write mode. And then when a failure recovers, this is the methodology that we use to bring that node back up in sync. If we suffer enough failures such that we no longer have a quorum of data shards available to satisfy queries, to satisfy update queries, we go into read-only mode and we return an error to the customer, to the user. Hopefully, though, folks have set up their clusters such that they've got enough spread that they're not going to suffer that many subsequent failures, right? So that's the reason for saying, you know, so many nodes in one region versus another region. This is intended to be a geographically distributed system. You can run all your nodes in one building. We do it frequently at TransLattice, but that does increase the chance that you'll have a catastrophic failure that sends you either into read-only mode or takes you down, right? If you lose power to the building and you don't have a UPS set up, yeah, you're obviously down. So we solve that, as I said, by spreading it out. Okay? All right. Probably should have switched to that slide earlier. So, okay, distributed recovery manager. The lock manager is made aware. There's not a lot of changes here, but again, he's made aware when there is a distributed object involved in the transaction to send that appropriate information to the nodes that house the nodes. Same thing with the transaction manager. Basically, very few changes, but he has been made aware that this is a distributed system so that he can act appropriately for transactions that are not local. Okay? And then we have the distributed transaction manager, which accepts the requests from the original client, right? He's essentially serving in that particular instance of that query. This transaction manager is acting as a slave to the original requesting node. So you may have multiple distributed transaction managers depending on how many nodes get involved in a query, and they eventually return all information back to the requesting node. Okay. So what does the user essentially see? I mentioned earlier, because it's MVCC, we still work in the same way that if you expect. If a transaction can be satisfied on a local node, we use the Paxos system to merely say, hey, I've got an update. Everyone else who has a copy of that particular row, see any problems with me updating? Everybody says, no, we're cool. The row goes ahead and gets updated. Okay. If we have a situation where we have an intervening or conflicting transaction, again, it works the same way that it does in Postgres. In this example, we have the same request come in, but at the same time, node 5 has also said, oh, I want to update that same row. Okay? So when that update comes through, because the snapshot is out of date, he returns an error to the user. Same way it works today in Postgres. Okay. Okay, so we break up the data. As I said, you can control the granularity of the breakup, but we can break up tables into thousands or hundreds of thousands of shards if we need to. And by default, this is along primary key lines. Okay? So, and as I mentioned earlier, again, customers don't see shards, users don't see shards, they see tables. And the underlying mechanism knows where all the shards reside and returns the results of the query appropriately. We can also use composite keys. If we have a composite key where the portion of the key, the first key column might be store or region, that might be an excellent key to shard on, especially if I need to do some of those locating policies that we talked about earlier. Okay, so how do I do this? We've added a partitioning clause to the create table. And this is the only change that we've made syntactically to the Postgres syntax. This may go away eventually when we figure out ways to more automate this. We added two key words, shard partition and shard mask. The shard partition tells us how many of the primary key columns to consider in our sharding, and then the shard mask is used to do a logical OR against those columns if we don't want a single shard per unique value. Shard partition will give us a single shard for every unique value that is defined by those columns. So if I've got a single column primary key and I don't use shard mask, I'll get a shard for every row in that table. So, okay. Oh, a couple of other things. Because of how we do our underlying storage, we do not support the table space clause. Okay, so if you do that, I'm told that bad things will happen. Apparently, engineers are afraid of scaring me, so they won't tell me how bad and what will happen. So,
why don't you just disable it?
and I think they probably have, and so it probably returns an error. I haven't tried it. Shame on me. So, but yes, it should, and I bet it does. A couple releases ago, I don't think it did. Okay. Another gotcha, if you will, is that primary keys are currently required, right? So if I have a table that doesn't have a primary key, you know, stick a serial on it. If it doesn't have a primary key because it's one of those silly 8K tables, why have a primary key on an 8K table? Just stick us on a serial, tell us it's not sharded. If you leave this clause off, it's one shard per table. So you don't actually have to change your schemas at all.
What's an 8K table?
I'm sorry, what?
What's an 8K table?
Oh, I'm sorry. A table that requires less than 8,192 bytes to store, basically a page size, right? There's no reason sharding itty-bitty tiny lookup tables. Yeah, because it doesn't buy you anything, right? I'm going to...
So if it's not sharded, does that mean it's copied?
Yes, 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 and yes. Even if it's not sharded, the system creates one shard that contains every row in that table, and it's distributed across the cluster according to your policy. So, okay, we talked about that. Okay. Identifies the specific columns. There's a couple of shortfalls in the current implementation. One, if I have a multi-part key, I can choose to partition on all the columns or the first n columns in the key. I can't say I want to use only the third column or only the last column for sharding, if I might want to do that. So there are some things you may have to think about, and you may have to think about how your primary keys are set up when you implement TED. Okay. Again, this just sort of explains it. Shard partition is looking at the primary key columns that I want to use for sharding. Okay. Hello. And then shard mask does a bitwise and on the columns that I've specified for my shard partition. This is in the instance where, say, I only have a single column key, but I have a 2 billion row table, right? I really don't want to have a 2 billion row table with one partition, right? Because there are very few applications that have billion row tables where every action that I perform, I want to perform on 2 billion rows, right? So with that, I can use shard mask, which will then just look at a certain number of bits for determining what is a unique value. So I'll basically block out the low order bits and use the high order bits for determining my uniqueness. Okay. In this case, because I've used a shard partition of 1 with a shard mask of 1, that basically says I want to split this table into 2 shards, odds and evens. Okay. And unfortunately, another limitation, if I had shard partition 3, shard mask 1, I would get 6 partitions because it's applying the mask to each column. So we definitely need to get some more control here and some more flexibility in our partitioning. Okay, so that's basically TED. And if you have any questions, I'll be happy to answer them. Not currently. And as to the question of performance, TED is slower. You do have some overhead in order to do the geographically distributed. It is not unbearably slow, and one of the key factors in TED is that because you're moving nodes closer to end users, and because we place data on those nodes according to usage, those users typically get better performance than they do in a centralized database, right? Because if I'm sitting in Frankfurt and I'm accessing a data center in Denver, every query I do has to traverse that entire distance, and every result set has to traverse that entire distance. In TED, I put a node in Frankfurt, I learn over time, or I've specified with my redundancy policy that I want data kept in Frankfurt, and so now those are local transactions. The cool thing about that is that as changes are being made in Frankfurt, I can see them immediately in Denver. And this is really useful for one of our customers that is a large banking institution that they currently have 5 data centers in 5 regions. They're restricted based on the types of offerings they can offer customers in the various countries, and they're restricted by where they have to keep data because they do a lot of business in Europe. And this is a bank. Unfortunately, with these 5 data centers, they cannot see a solid state of their business for 24 hours. The whole replication and reconciliation process is a day behind for them to see their business, which means a lot of their international customers have figured this out, and they figured out how to game the system. I can do a large transaction through my Frankfurt subsidiary at this bank at the same time doing a large transaction in New York against this bank, and they're not going to know it for 24 hours. With TED, that can't happen, because as soon as that transaction occurs in Frankfurt, London's aware of it, New York's aware of it. They can see the current state of their business every day, any hour of the day. So.
I kind of misunderstood how the client works. So if you just connect to any one of them and you can ask for your data.
Yes, you connect, and you actually connect to this service entry point, which is an abstraction. Right? So I always connect to this IP address, and this IP address says, who's going to grab this? And one of the nodes in the system grabs that request and services it. You don't necessarily know where the specific node that you catch is. Again, we try to connect you to the closest node and the node that has the most data that can satisfy your request. Boy, I wish I could answer that. I will ask Marcus. Okay.
Because if I look at the Paxo protocol, it also only distributes basically the whole write request at the end at commit transaction time. And that was exactly the Postgres-R problem, that a long-running transaction, if short-running transactions in the meantime committed and conflicted with some of the rights, that the long-running transactions always got aborted and never succeeded. And that there was a level at which the transaction volume in Postgres-R basically prohibited all long-running transactions, and they never succeeded.
Right. There has been substantial rework done on the Paxos algorithm, because you're right, it was problematic in Postgres-R. So we are now currently in the 4th rewrite of the Paxos algorithm because we continue to fine-tune it and improve it and make it less chatty. One of the problems with the original implementation was In the first place, I believe Postgres-R was originally built with classic Paxos, and that is extraordinarily chatty and probably far too chatty to try and build an ACID-compliant database with. And so we've switched to fast generalized Paxos and made some substantial performance enhancements to it. And so in the next release, we'll have the latest rev of our Paxos.
So you're doing one Paxos request per transaction, isn't it?
There is one Paxos request for all outstanding transactions on the system. So, as I said, we keep a partially ordered list of all transactions in flight. The nodes are all aware of the transactions in flight, and anything that can commit in the current round of the Paxos negotiations commits.
You mentioned 2 billion record tables, which may distribute by geographical location, and each have multiple nodes, and it's distributed to tons of hard drives or whatever sense. And single failure, if it's one physical drive or set failed, how you do recovery in this case? Because it's your 2 billion is distributed everywhere to 100 hard drives. What's happened if it's happened? What's happened if it's failure happened? And what recovery mechanism was that?
Okay, I'm not sure if I caught all of that, but if you've set up your policy so that you have a certain number of copies, and copies should never be one, and probably should never be two, because we need a majority of copies available in order to maintain write operations throughout the cluster. So when a disk drive fails, okay, there is another copy of every shard that's on that drive somewhere throughout the rest of the cluster. Okay? Some of those shards may get updated while that disk drive is down. When that disk drive comes up, the system will send out a broadcast. What did I miss? And those shards that were updated in the interim will propagate to that disk. And all the shards, all the nodes that maintain a copy of that throughout the cluster will participate in that recovery so that it's amortized over the nodes in the cluster. So we minimize mean time to recovery that way.
Okay, and in that case, if your number of copies lower than 3, so you have a voting mechanism, because your voting mechanism is based on number of updates, right? So if it's you not hear me? Well,
Yeah, I'm having trouble hearing you. Sorry.
I will try louder. When your voting mechanism is based on majority,
Yes.
and if you have only 2 copies, if you have 3 copies, one is failed, how you make decision what voting mechanism start to execute it, because you have.
Well, if I have 2 copies, I have a majority. And so all transactions continue to run as normal, right? And then when the third copy comes back, he sees that, oh, there's a newer commit ID stored on the system. I'm behind. So somebody catch me up, right? And so he will stay. He will not go into full operation until after he's fully recovered.
So if you have 2 copies and you have 2 conflict requests,
Mm-hmm.
one goes to A, other goes to B, and there's only 2 you have on system, and A, B.
Right. That's where the Paxos algorithm works. When both those requests comes in, it sends the request to the node, says, can I do this update? And you'll get and one of those transactions will succeed, and the other one will return back, essentially snapshot out of date. Snapshot too old. Okay, I think time's up. Thank you very much.